The second part of chapter 22. And here we are going to talk about Gauss's law and how we're going to apply it to and connect it to the idea of the flux, and also how to actually calculate the electric field. And just a little bit of Gauss. He was a scientist that was able to help in developing several branches in mathematics, including differential geometry, real analysis, and number theory. And one of the most important inventions is the bell curve in statistics. Gauss also made state-of-the-art investigations of the Earth magnetism, and he calculated the orbit of the first asteroid that was discovered. I will say here, Gauss's law is another way, very similar to Coulomb's law, to calculate the electric field and express a relationship between electric charge and electric field. It's working very good with I will say, maybe I will add this, like Gauss's more general, and it has provided a method for us to calculate electric fields easily for charge distribution. It works also when we have symmetry in the things that we are talking about. Now, if we will look at here point charge that is centered in a spherical sphere, we're gonna see that the area, it is just kind of going out of the surface. And we have here two surfaces. One of them we call R, like this is the small circle, and this is like two R's. And we will say here that the area element on the larger sphere is 4 times dA, because because it's pi r 4 pi r squared, then therefore it's gonna be, you have like 4 of that area. And now the electric magnitude now is going to be that is the second surface is going to be 1/4 as great. And therefore the electric flux is the same for both areas, and it is independent of the radius of the sphere. We said that before when we were talking about boxes. We said like the size of the box doesn't affect the magnitude of the electric field. And actually that's a surface that we're going to add, which is Gauss's surface, is arbitrary. Like you can put it anywhere, but of course it's going to be in the region where you want to calculate the electric field. The flux also is depending only in the charge enclosed. Now, Gauss's law in a vacuum, when we have vacuum, we can say if I have a closed surface and there is no charge, then phi, which is the electric flux, it is d dot dA equals 0. And the figure shows a point charge outside a closed surface that encloses no charge. And then we said the number of electric field lines that is coming into the surface equal the ones that they are leaving. And therefore is going to be 0. Now, when we have a charge, then the total electric flux through a closed surface is equal to the total net charge inside the surface divided by epsilon 0. And this is Gauss's law. Theta E, it is the electric flux through a closed surface, and this is really for a surface that has an area of A, and it's a surface integral. And a Q enclosed is the total charge that is enclosed by that surface, and epsilon 0, it is the electric constant that we were working with before. In the case of a single point charge at the center of a spherical sphere surface, Gauss's law follows simply from Coulomb's law, and we can easily say that if we have a surface around a positive charge, then it has an outward flux, and easily you can say here that like E times A should equal the charge enclosed, which is Q over epsilon 0, and all we can say A, it is okay, here cosine 0 is 0, of course, is 1, sorry. Okay, then here is going to be Q over epsilon 0 over A, and A here, it is 4 pi r squared and times epsilon 0, and this is really the results that we have from Coulomb's law. It's the same idea, okay? It's the same for a negative charge. Here, applications of Gauss's law without having to do any integration, we can use Gauss's law to determine the electric flux through the closed surfaces in the diagram. Then it's gonna give us another way of doing things, maybe like I would say easier. And here I will say we have in this drawing so many surfaces, like here A, the red one, the blue is B, and then C is the purple, and D is this region only here, and E it's here. And if you look at phi, which is EA, okay, I will say is gonna be enclosing just the charge that is inside A, which is the plus Q divided by epsilon 0. If I will say the electric field at, oh sorry, not E, there is no surface called E, this is the electric field. Okay, for B, it is just the charge here, which is negative. If I will go for C, the purple is the C, then it is 0, because the net charge, these charges are equal, then negative Q plus Q, it is 0. And if we go for D, D, it has no enclosed charge, and therefore the electric field is 0. This is the problem-solving strategy using Gauss's law. We have to list the known and unknown quantities and identify the target variables. We also here should choose the size and placement of the Gaussian surface. As I said, because sometimes we might ask, like, okay, inside the sphere, outside the sphere, at a distance maybe very far from the sphere, and therefore you need to know what is really the approximate size of and where it should be located. And also I will say we need to evaluate the integral then, which is the the E perpendicular times dA. In this equation, we have the electric field component that is really the one that is perpendicular, and that one, it is gonna be using most of the time that integral is gonna be like very easy to calculate, because you need only to replace it by what is really dA. If E is perpendicular, normal to every point at the surface with the area, if it's points outward from the interior of the surface, and if it has the same magnitude at every point, then E, that is going to be E constant, and over that is equal to E times the the area. And here also, if like that surface is if it is inward, then the vertical component of the electric field is negative A, and then the integration is going to yield negative EA. If E is tangent, then no flux, then E perpendicular is going to be 0. It's very easy to deal with it, even with if there is no charge within the Gaussian surface. You don't have to do anything, and then it's gonna be 0. Okay, let me show you how we are, like this is application of Gauss's law. We place a total positive charge Q on a solid conducting sphere with a radius R. Find E at any point inside or outside the sphere. Now, whenever we have a conductor, this point, you should know this, then I will say the charges, they're gonna repel each other till they accumulate at the surface. There will be no charge inside the sphere. It's just gonna be on the surface, because it's a conductor. If it is a non-conducting, then I can have the charge distributed all over the places. And here we place a total positive charge Q on a solid conducting sphere with radius R. Find E at any point inside or outside the sphere. Then inside, I would say no enclosed charge, of course, then E times 4 pi R squared. This is my surface, which is the Gaussian surface. And because Q enclosed is 0, then E is 0. When R is gonna equal to the radius, then I will say my Gaussian is gonna be here. This is really the center. This is R, and therefore I can say that E times 4 pi R squared equals Q over epsilon 0, and then E, it is Q over 4 pi 0 R squared. And these are consistent with the results that we got from, the integration that we did in chapter 21. Okay, now here, for outside the sphere, I can have now my surface outside here with a radius R, and then I will say E times, should be 4 pi R squared, because this is the surface area of a sphere, equals a Q over epsilon 0, and then this is the electric field. Also, I can do the same thing with a uniform line charge, where lambda is given as charge per unit length, and then electric charge is distributed uniformly along an infinitely long thin wire. The charge per unit length is lambda, assumed positive. Find the electric field by using Gauss's law. Of course, we know here that the electric field lines, they're gonna be going this way, all right, because it is positive outside like this. And when it comes here, they are parallel to the surface. Then the Gaussian surface here that I'm gonna take, it should be I will say, providing the same symmetry that was provided by the object. And here I will use a cylinder, and the Gaussian surface here, it has two flat ends where I will have the electric field lines are really parallel to the area. Therefore, I will have no contribution from the ends. For the curved surface, E and A are in the same direction, and therefore it's going to be EA cosine 0, which is 1, equals Q over epsilon 0. Now, if you look at this rounded, it's gonna be kind of I will say rectangular, okay, a sheet, where this is gonna be L, and that here is gonna be the circumference of the circle. Therefore, I will say the area of this one is gonna be 2 pi R times L times E. And here I have the charge enclosed. It is lambda times L divided by epsilon 0. Then E is going to be 1 over 2 pi epsilon 0 lambda over R. And this is the field of an infinite line of charge. more here, like showing you just if we have like kind of something like this, and suppose we construct a Gaussian surface inside the conductor. E is 0 everywhere, as we said. This is here the problem that I solved to you. Also, we can use Gauss's law to find the field of an infinite plane sheet of charge, and that is sigma over 2 epsilon 0. That sigma, it is, we call it like the surface charge density. Okay, and that one is actually one of the formulas you will use in the homework, and you will use also as well in the maybe exam. Here we like charges on conductors. We said that the charge is gonna reside entirely on the surface of the conductor, and then I will say E will be 0 within the conductor. Now here, for this here, if we have that same thing, but we have a cavity and we put, another charge inside that, then the conductor is uncharged and it is insulated from charge Q. According to Gauss's law, the total there must be a charge negative Q distributed on the surface of the cavity, drawn by this charge here, and the total charge on the conductor must remain 0, so the charge plus Q must appear in its outer surface, because these here, they're gonna cancel each other. This is here an experiment done by Faraday, and Faraday's historic ice pail experiment. We mount a conducting container on an insulating stand like this, and then the container is initially uncharged, and then we hang a metal ball that is charged, and of course we need an insulating thread so that the charge will not leak, and lower it in the container. And when it is lowered, of course, charge will be induced in the container as shown here. Okay, induced mean is gonna be the negative of that, and on the outer surface is gonna be positive. Charge ball induces charges on the interior and exterior of the container, and then I would say we now let the ball touch the inner wall, and the surface of the ball becomes part of the cavity surface, and then according to Gauss's law, the ball will lose all its charge, and finally we pull the ball out. We find that it has indeed lost all its charge, and I would say all the charge moves to the container's exterior because it is made of metal. Van de Graaff generator, it's a device that we use for generating charges, very similar to the introductory picture, where we have here the dome is gonna be like having charges. It operates on the same principle as in Faraday's ice pail experiment, and it can create charges. There is something called electrostatic shielding, which is a conducting box that is immersed in a uniform electric field, and the field of the induced charges on the box combines with the uniform to give a 0 total field inside the box. Then it's safe. Inside it's safe. We don't have any electric fields, and this is really here showing you the electrostatic shielding We have an object that we want to protect from electric fields. We surround this with a conducting box. We call that Faraday's cage. And we have like an external electric field that is going to make the electric field inside zero. All right, this is here. Also, Gauss's law can be used to show that the direction of the electric field at the surface of any conductor is always perpendicular to the surface, and the magnitude of the electric field just outside the charged conductor is proportional to the charge density, which is sigma divided by epsilon zero. Okay, these here are the problems for the homework, and I have here two more problems that I did solve. Like, I want you to check that solution for this is checkpoint 3, and this is checkpoint 4, and this is checkpoint 5. Okay, I have the solution, and I will upload the notes for you as soon as I'm done from this lecture. Thank you very much, and have a great day.